Good afternoon. I invite you to today's lecture. Today's lecture is about pipelining, about the speed up of our simple processor design, which we have seen on our third lecture. So it is fifth lecture. We have seen a memory during the last one. And the first, we look at the actual design of 2011, 12, and so on, processors. So there is one interesting architecture from AMD. It is Amd Bulldozer. It was not so useful architecture in the speed. Today reasons are much more powerful. But what is interesting to see on this architecture that we can identify different parts of the CPU, and it has L1 cache for the instructions. So basically instructions are taken from main memory to the L1 cache, as we have already spoken about during the last lecture. Then we have there a unit which fetch instruction and predecodes them, and then they are decoded and up to 4 instructions, x86 instructions, can be decoded in parallel. For x86 instruction, it is quite complex to decode them because they can have from 1 to 14 bytes, so it is relatively complex task. And there is a double decoder. Each of those decoders has a fast path where it can convert directly the instruction to a RISC-like instruction, or if there is the instruction more complex, then it is a decode to a multiple that real machine instruction which are running inside the core of the processor. Then there is some execution, dispatch and execution units. And what is interesting on this complex design is that we have there up to 4 parallel instruction execution for the integer, arithmetic, and access to the memory and so on. And we have those integer channels doubled because this CPU is able to decode the instruction from 2 instruction streams. So in the fact that single core on the chip behaves as a 2 processors from the software point of view. So basically the units can be utilized even during the time when the execution blocks on the access to the main memory and so on. What is interesting on this actual architecture is that floating point part of the CPU is shared between both execution cores. So we can execute 2 programs in parallel. Each of them has its own general purpose integer register file, but the floating point registers, renames, and so on are shared between both execution cores. So it is interesting design, and you can see how complex the processor today is, and so on. And actual data accesses are through the L2 cache, and then there is access to the external bus. So this maps to the components which we have seen already during our past lecture. Then there is another example for Intel Nehalem architecture, Core i7. So basically, again, there is some connection to the external memory. So there is a memory controller. Then there is 8 megabytes shared cache between all cores on a chip. And then there is a L2 cache, 256 kilobytes, and it feds data to the instruction L1 cache. Then those instructions are fetched on the 16 bytes basis. Then they are somehow aligned to match somehow a decoder queue. And in this case, we can decode up to 4 instructions, but only one of them can be a complex one which produces a multiple RISC-like operation. And other instruction has to be a simple. And then we can macrofuse instruction and so on, and then we dispatch them to the multiple execution units. So there is one arithmetic logic unit, another, those two can work even as units to compute the addresses to the data memory. Those units are only arithmetic logic unit. This one has additional FPU, this one has additional FPU, floating point unit. So this is the actual architecture, and we show how such complex processor works on the advanced computer architectures course. Today we focus on much more simple CPU. So we return back to our third lecture, where we started with the simple RISC-V processor. And we have implemented a set of arithmetic logic instructions which works between three registers. So they have one source register, second source register, and destination register. Or we have there the instruction which can add immediate value to the one of the registers and store the result in the destination register. And then we have there load word and store word to access data in the memory, where load word has one source register, immediate operand which is added as the offset to the address in the register, and then the destination register. So it has same encoding, the I type, as added I. Only it access memory, added I bypass the memory stage. For the store word, there is a exception when we compare it, for example, with a Mips instruction set, because in this case we have one source register where we want to add the immediate operand, and another register which is again the source of the value which will be stored to the memory. And in this case, the encoding is a little irregular, that basically we use two source registers, so they are kept on their position, and destination register is not used for the store word operation because destination is the memory. So we can reuse that area for the rest of immediate operand. Then we have there a branch instruction, and branch instruction needs a two source operand, so it is similar to the store word, but it doesn't need to provide branches to the odd addresses, because each instruction is at least 16 bits long. So for this reason, there is reuse this bit 11, this bit 7 as bit 11 of the target branch target offset. So it is the encoding of immediate operands on the RISC-V is relatively complex, but thanks to this complexity, we can keep a destination register, first source register, and second source register exactly at the same position for all types of the instruction. Then there are the instruction which allows to set upper 20 bits of the register, because we cannot encode 32 bits to the 32-bit instruction when there should be some space for opcode and the rest. So we have there that special instruction which can set upper part of the register. And then we have there some instruction for the unconditional jumps and subroutine callings. We left those for some of the later lectures. And now we want to make this CPU a little faster. So again, we return back. There is our CPU. We have already seen that basically we have program counter. It sets the value, it chooses a location in the memory. There we read the instruction. Instruction provides the information what is the operation which should be processed to the control unit. And those bits select the first register, those bit 24 to 20 select the second register, or some of those bits are decoded through the immediate decode unit, so they provide offset, for example, or immediate value. Then we have their arithmetic logic unit. output of arithmetic logic unit can be used as an address to store the second source register as the data to the memory, or the output can be used directly as the result of the operation and passed directly to the registers. And the register to which we want to pass computed data or data read from the memory is selected by the bits 11 to 7. We use this notation from the higher value down to lower one because it is how we use it in, for example, VHDL or some hardware description language. So this is the reason. Okay. And there is one change. In the previous lecture, we have that 11 to 7 put directly here to specify directly from the read instruction. Now we have exactly same circuit, but we pass a data value or the value of destination register that it goes together with the actual data which should be put into the register, and then there is an operation which selects that we want to write to the register. And if we look at this design, then we see that there is a problem, because at the moment when at the next clock cycle we add the 4 to the instruction and store the new value to the program counter register, then we need to wait till the whole combinatorial logic stabilize on the final result. So basically we need to wait till the program counter is set, and there has to be some delay after the program counter set, because it is not immediately provided on the output of the program counter register. Then there is some time to access the memory. Then the instruction is read, and it takes some time to decode it for immediate value, which is probably shorter than the time before we read the value from the register. So we need to add the time for propagation and reading the register. Then there is a time to compute the actual result on the arithmetic logic unit. Then in some case we directly go to the write back, but for some another instruction we set the address and need to wait till the actual location in the memory is found, basically when the decoder selects the correct word line and bit line and so on, and it is set to the output. And then we need to provide some time to select the correct output if it is bypass or memory, and with some time reserved for the register file to store the value, we need to provide a stable value here before we advance the CPU to the next clock cycle by the next positive edge on the clock signal. And at that clock signal, again, we get a new address of the new instruction, and the main CPU cycle can continue. But it is a problem. So if you look here for this example design, when there are some times for the propagation through the registers and so on, we get the final time to propagate the signal with some reserve through whole that logic as little more than 1 microsecond. So this means that at most 1 million of the instruction can be executed per second. And it is relatively slow, because you want to execute something like 3 millars of the instruction per second or something like that. So it seems that this design has a significant problem. So the first thing which we can do is that we separate the instruction fetch from the actual instruction execution. In this case, that long time, to read the memory, 300 nanoseconds, which is longest one, is not included in the single clock cycle twice, once per fetching the instruction and once for the actual execution and access of the memory. So basically, in this case, we add there a register here after the instruction is read. So each clock cycle we select the address from the program counter, read the value of the instruction, machine instruction, and store it into the interstage register, fetch buffer. And at the next clock cycle, we already start to read instruction +1, but we execute the instruction I. So the previous instruction is now decoded, executed, and eventually reads data from the memory. So in this case, we do not need to fit into single clock cycle 2 reads from the memory. Only the one, and in the next clock cycle, the another one. So in this case, we can speed up the execution because now the longest path inside the CPU is that execution path on the second half, and we have there only the ones that long time of access to the memory, and there is not setup time for program counter and so on. So in this case, in this actual design, we get to something like 1.5 megahertz or million instruction per second. So this is the first speed up. But at this moment, when we use such speed up, we have one problem. If we have there instruction which branches, then in the fact the actual branch instruction get to the execution one clock cycle after the following instruction is read, because it is fetched in parallel with the execution of this instruction. So in this case, we have a trouble that we have already fetch instruction, and we are not sure if a branch doesn't select a different path, so that we in the fact should skip that instruction. One option is that we flush such instruction, which is fetch. Other option is that we allow so-called delay slots. So for example, if you use a DSL modem to connect to the internet, then it typically uses on the switching station, it usually uses DSP, digital signal processors, and those quite often use this technique of delay slots, and it is on the compiler to decide what would be put into the delay slot. So basically, after the branch, there is one instruction which is executed unconditionally, even if the branch decide to skip the rest of the instructions. But we, for example, if we have there some increment of some pointer to some vector and so on, we quite often can allow this increment to be run unconditionally. So if it is before the branch, in the fact, we can put it after the branch, and if we know that actual decision of the branch is delayed by one instruction, then we allow this one instruction to be executed after the branch. So there are more examples what we can do. So basically, for example, if we have there instruction which doesn't directly influence a branch condition, and it is before the branch condition, then we can put such instruction after the branch condition. And it is executed unconditionally. The rest of the instructions is skipped. Or other option is, for example, if we have there operation which can be executed, and if some following instructions are skipped, then its result is of no use, basically. It doesn't make a problem that we have executed one more instruction which effect is in the fact eliminated because we skip the rest of the code. So in such case, we can move the instruction from the if-then branch to the delay slot and left it to execute even that its result is not used. Same here when we have there some loop, and we have typically there some operation which adds to the pointers or something like that, we can we can put it into the delay slot, or if this instruction here, in this case, influence the variable which is used in the branch condition, but we have there the instruction at the start of the cycle, then we can move this instruction out of the cycle and put the copy after the if statement. It is executed even when we leave the cycle, but in some cases it has no change on the actual result. So we can use a delay slot. It is how, for example, a Mips architecture defines the execution, that one instruction after the branch is executed unconditionally. Today processors, which has much deeper pipelines and so on, would need to execute a multiple instruction in the delay slot, and for this reason it is not in use today. So now we return again to that Mips design. We look at the designs and examples which are in the fact easy. It is something which has been invented in 1980 by Professor Hennessy and Peterson. As I have shown at the start, today's processors are much more complex, but we try to analyze a simple processor design, pipeline processor design. So we have seen that the time to execute a whole single instruction is too long. So we can divide actual execution to the parts when we fetch the instruction from the memory, set up the program counter and fetch the instruction from the memory. Then we decode the instruction and read the actual operands from the general purpose registers. Then there is the actual execution when we use arithmetic logic unit, do the addition, we need that carry look, a hit logic, and so on. Then there is a time when we access a data memory, and then a last phase or stage when we store a result back into the registers. And this division to 5 phases, 5 stages is quite often used. Okay, we can have up to 20 or maybe even 40 in some CPUs, but that 5 is relatively easy to understand. So what we have gained if we divide the processor execution into the multiple stages. For example, imagine that you have a hotel and you want to do a big laundry. So basically to clean the rooms and so on. And you have a washing machine and you have a drying machine and so on. If you take one set of the stuff, of the clothes or something, and put it into the washing machine, wait to the end, then move it to the drying machine and so on, then it takes a relatively long time. But if you can do those operations in parallel, basically that you hoard the stuff on some pile, then you move it and put it to the washing machine, take it out, and then put it to the drying machine, and in between put a new load to the washing machine. Then in the fact your throughput is enhanced 2 times. And you can go up to more steps. It is exactly how the car production works. You have the pipelines production when one team is putting together the base, another one is putting engine inside, another one is putting seats inside, and so on. And if you do it all on one car, then the teams needs to wait till the previous team finish the process and operation. In the pipeline, you basically do the single operation, and the half-produced car, you move to the next stage and do next operation. So we can do exactly the same with the instructions. So we fetch the first instruction, but we only fetch it and do not decode it. Then in the next clock cycle, we pass the instruction to the decode unit, and in parallel, we fetch a second instruction, and so on. First instruction accesses execution, arithmetic logic unit, and at this time we fetch the third instruction, and so on. We pass those instructions through the units, and if we have a 5 stage in the pipeline, so there is that actual store of the result into the registers, which maybe it should be a write back, it will be better. Then, in the fact, the first instruction, which needs to go through all the stages, is executed in 5 clock cycles. So, even that we have a shorter operation and we can increase the frequency of the clock, so in the ideal case, we can increase the frequency 5 times, because we divide it in 5 small operations, the processing of the instruction. The actual first instruction is executed exactly in same or even longer time than for the single cycle processor. But for the second instruction, it is finished 1 clock cycle after the first one. And for the third one, we finish the execution again 1 more clock. So if we have a pipeline processor and we say that tau represents the clock cycle period, then in the fact, the first instruction needs a k stages, so k times a tau, but each next instruction, so if we want to execute an instruction, then for the n-1, that following instruction, we only need a tau for each another instruction. So we have speed up the execution. If we compare the result, we compute the speed up as a ratio between the time required to execute the n instruction on the single cycle CPU divided by time on the k-stage pipeline CPU. Then in such case, in the fact, for the single clock cycle, we can simplify that we need a time of k tau to execute all those stages. So basically we need this time, but we need all this time for each of n instruction. But for the pipeline version, we need that longer time only for the first instruction, and rest can be executed in that single tau time. So in the theory, for the big sequence of the instructions which can be executed without interruption, the speed up of the pipeline processor can be equivalent to k, which represents a number of pipeline stages. Again, this is a real example. This is for a micro-Mips architecture, I think, and you can see that the execution time of some instruction fetches, registers, and so on takes this 800 picoseconds. And when we want to start another instruction, that it starts and again takes 800 picoseconds, and so on. But at the moment, when we interleave the operation, when we use a pipeline, then in this case, we can, in the fact, interleave the operation because memory access doesn't take more than 200 picoseconds. So in the fact, we can increase the clock frequency and reduce a clock cycle time to 200 picoseconds. So in the fact, to speed up the processing by 4, not by 5, even that we have 5 stages, because some of those times are not divided equally. It is there is a difference that some register read takes a short time. So in the fact, if we divide it to the parts, it doesn't help so much in this case. So, but we have a speed up by 4, which is not bad. Problems is that at the moment when we execute the instruction in this pipeline way, that there can be interdependencies between the instructions. So it is possible that one instruction requires the results of the preceding instruction, but the instruction latency to finish this execution is 5 clock cycles, for example, for file-level pipeline. So in this case, if we start to execute the next instruction directly in the next clock cycle after the fetch of the instruction, then we get into the read after write hazard. So it is a problem. Another problem is that if we start to execute a multiple instruction in parallel, or if we allow a finish one instruction earlier than another, then we can get to the another problems. We can get to the state, for example, when we modify a register to one value and then to second value, but in the fact because the second instruction is finished earlier than the first one, then so we have first instruction, it finish and sets a R2 equal to, for example, 1. Then the second instruction, which should set R2 to 2. But if this second instruction is executed earlier than the first one, then in the fact it sets a R2 to 2, but later R2 is rewritten by the 1. So you see that the incorrect result is stored as a final value in the register. Another problem is that you can have a write after read hazard, which again swaps the operation between the registers. But it is a problem of the architectures which are able to execute a multiple instruction in parallel and finish them out of order. So this is for advanced computer architectures course. So we return back to the simple pipeline solution. So in this case, the instruction would be retired, finished, completed in the same sequence as in the program. But anyway, even this is quite complex, so we will see what we need to do. Another problem is that we can have a structural hazard. For example, we can use some other to add the, for some instruction to add in the decode phase, and for some another instruction to add two values, for example, in the memory phase. In such case, we have so-called structural hazard because a given unit is necessary inside 2 stages. But it is easy to resolve this problem. It can be resolved such way that we duplicate the given unit, the given the given component. So it can be resolved by the duplication. But those read after write hazard are a little more complex. And then we have so-called control hazard. Control hazard is that we want to control where the program should continue by the branches, but the execution of the branch takes some time, and in between we have read and started to execute some instruction which in the fact should be skipped. And problem is that as we make a pipeline deeper and deeper, then those problems start to be more problematic and more complex. So we return to our simple case when we have a 5-stage pipeline. And in this case, we write a data to the register in the write back phase. If we define that we are able to read the registers, new value from the registers, at the same clock cycle as they are written into by the previous instruction, then if we start to decode the next instruction in the second or in the third clock cycle, so basically we have there add from x2 to x3 to the x1, and then we want to subtract x3 from that value, Okay, this code has no sense because in the fact it copies x2 to x4, but it is an example. But there is a problem that there is a dependency read after the write to the register x1, and we have the value in x1 at the write back time, in this time. So we have a problem that if we now wait for the, we need somehow to wait till this previous instruction is finished. And if we do not wait, then we read an incorrect value from the register file and we get into the troubles. Okay. For the control hazard, we have there a problem that we have there a branch, and if we execute and evaluate condition in the execute stage, and actual branch is processed in the memory stage, then a program counter is set on the next clock cycle, and only this instruction in the fact at the 5th clock cycle after the start of our instruction start to fetch instruction from the correct location. So in this case, we have a problem that in the fact we have executed 3 instructions which are incorrect. So again, we need to think what we do with those instructions. Okay, so we now know that there are a problem to implement the pipeline processor, but we hope that the speed up prevails and that we go for those troubles. So we have there a non-pipeline version, as we have seen on the previous lecture, except that we provide the actual target register address, destination register address, as this long wire which goes together with the data which we want to store to given register. And now we try to divide the CPU to those multiple pipeline stages. So we add there interstage registers. So basically this one is from instruction fetch to instruction decode. This one is from the instruction decode to the execute. And this one is from X again to mem. And this one is from mem to write back. So what happens? In the first clock cycle, we read the instruction. In the second one, we decode it. We find what is the target register, destination register. Then in the next clock cycle, we copy the results read from the registers to the interstage register, so it keeps the value. And we can decode the another incoming instruction. And now we process the instructions through the arithmetic logic unit. And this first one, and the second one is decode. We compute the values and they are stored into interstage register and so on. And after 3 clock cycles, the value which starts here is modified and written back to the register file. We see that that value needs a 3 clock cycle because at each clock cycle it propagates or it is stored at the next interstage register. So we need 3 clock cycles till the value and the corresponding information to which register it should be stored is its targets or propagates to the write back phase and is stored in the actual register file, yes?
So can you just repeat one more time what happens after it leaves the ALU?
After the ALU is left by the data, then the data are stored here. So basically, in 1 clock cycle, we get to this interstage, and it is held here. Then on the next clock cycle, we compute from those values, for example, the addition, and we store the result here, and we again remember what is the destination register. And then on the next clock cycle, we get from this interstage and propagate the value, for example, and read the value from the memory and store the information about a destination register. And at the last one, we get the value and store the results in the register file. You have a new version of our Qt Sim simulator now, so we have updated diagrams in the simulator, so you can exactly analyze what happens in the CPU. We have reserved for this next tutorial on the next week tutorial will be on the pipeline execution. Okay, so in this case, we see that it takes 3 clock cycles before the value is modified and stored back to the register files. For sure, if we have 2 instructions in our pipeline design, which is a scalar, so it doesn't allow to process a multiple instruction in the parallel, we are sure that 2 instructions are not in the decode stage together. So one is in the decode stage and one is in the execute stage. So in this way, we have there in the fact natural delay when the next one instruction which needs a data is 1 clock after the previous which generates the data. But even that is not enough because data are not there when we pass the instruction to the next stage. We will see the examples for this. Okay, so it is our pipeline design. If there is no interdependency between instructions, then it can work quite well. We need to add a logic for decoding the instruction and actual control of the CPU. So we put there a control unit. And it is exactly the same control unit as for the single clock cycle processor. But the actual control signal has to be delayed and pass together with the data for which they are valid. So as you can see, same as we delay the information to which register we want to store the result, same way we need to delay information that we want to write a result into the register. So we need to delay it and add there this connection. Same for the decision, for example, if we should take a value from bypass or from the memory. So again, this needs to be delayed by, in the fact, 2 or 3 clock cycles from the time when it is decoded on the control unit. So we need to register those signals. And we can redraw again our CPU. It is exactly the same picture, but we will need to add some more logic there. So it is the reason that we have make it a little smaller in this case. So we have there even that branching and so on. Branch is decoded in the memory stage, and the target address is again delayed and computed in the memory stage. So at this time, we can control, for example, if we want to continue with the next instruction, which is following the sum of the instructions which has been fetched in the loop, or if we want to switch to some another destination. But we will have there problems with hazards. We look at it a little later. So basically, what happens here? We have there the add instruction, which adds to register as 0, and then the AND instruction, which takes the value from S0, combines it with some independent S1, and stores the result to T0. Then the OR instruction, which combines S1 as the second input with S4. And the third one, dependent instruction, which computes T2 and takes S0. So we can see that S0 is, if we go to the first clock cycle, in the first clock cycle, we fetch the add instruction. In the next, we decode that we need S2 and S3, so they are here. And in parallel, we decode or we read the instruction fetch instruction AND. And And in the next cycle, we compute the actual addition of S2 and S3. But the S1 is already required by the AND instruction. And our actual add instruction still needs to propagate through the memory stage, and only in the 5th clock cycle it is stored at the start of that cycle in the register file. So in the fact, we need the value of S0 at the 3rd clock cycle, but we have it in the register file in the 5th clock cycle. So we are in the troubles now. So it is a hazard because we read there an incorrect value from the register file. Same for this one. It needs for the second input operand S0, but S0 is known one cycle later than we have read the value from the register file. So we read some previous value which is incorrect. For the last instruction, it is decoded, it is fetched and decoded in the 5th clock cycle, and we have defined that our register file is able to accept the write, and if we write to the register which corresponds actually to one of the registers which is read, then in such case the value is propagated to the output, so that this 4th instruction, subtraction, is executed correctly. But those two previous instructions are executed incorrectly with incorrect data. One option is that you learn the programmers and compiler to not put interdependent registers into next 2 clock cycles after this instruction. But it is quite a big problem, and in the fact it would slow down the CPU. So what we can do, this is the actual screenshot, or in the fact vector print to the vector format from our simulator. So you can see there is the add instruction which should add the registers 2 and 3. Register 2 has 2, 2, 2, 2, 2. Register 3 has inside the value 3, 3, 3. On the arithmetic logic unit, we have the output 5, 5, 5, 5, which is correct result. But the actual follow-up instruction that end from our previous sequence is already requiring to read the register S0, which is a physical register 8. Those S are those mnemonic names for the registers. So S registers are for local function variables, T are temporaries, A are arguments, and so on. So in this case, the S is exactly the physical register X8. And we see that this X8, here, it is marked by the red, is equivalent to the destination register 8 of the instruction which is in execute phase. But because it has not yet reached a write-back phase, then a value in the register file which is read is still initial value 0. So if we continue the execution at this moment, then we get incorrect result. Correct result is that we should add a S1, which should be a 1, 1, 1 with 5, and we should get a 6, 6, 6. But we do not get it. But we can find that there is this situation that we compare which register we want to read, and that in this or in this stage, there is still a request to write register of the same index. So at this moment when there is this situation, we can add there a hazard unit which informs, no, there is a problem. So we need to postpone the execution of these instructions which are at the start of pipeline till this instruction propagates to the end of the pipeline. So you can test it on our simulator. There is an actual path to the stat support repository where you have an actual example which I have there. So I step forward, and in this case, we need to wait 2 clock cycles till our instruction, which adds to the register x8 or S0, provides that value here as 555. There is that we want to write to the register 8. There is still information because this operation is stalled. It is basically kept at this stage. So in this case, we know that there is a request to read register, physical register 8. Write to register 8, that it is written, it is shown here. So basically in this case, we know that we can propagate the information from the written register to the read register, and we get a correct value 555. And in the next clock cycle, this instruction advances to the execute and adds this with 111, and we get a correct result 666. But it has a disadvantage. If we use this stall mechanism, then in the fact, if there are many interdependent operations, then in the fact we need to wait after each operation 2 clock cycles till we have a result. So if we have many interdependent operations, then in the fact we have hopefully speed up the processor by the dividing execution to the pipeline stages. Maybe by something, if we have 5 stages, then the result can be something like 4 times faster or 4.5 faster. But then we have a divider speed by the 1 active instruction and then 2 stall cycles. So we divide it by 3. So as you see, the result is that we have not speed up our processor too much. In the worst case, maybe that there is another case when the instructions are not interdependent. But we can do the other thing. If you look what happens inside the processor, then we see that in the second clock cycle, we have added those we have read those 2 registers. And in the third clock cycle, we already have this value here. We already know that there is a value 555, which should be provided to the register S0 in the 5th clock cycle. So if we can detect this situation, then in the next clock cycle, we can in the fact forward the information to the, and it should be, okay, there is a mistake, it should be to the S0, to this one. The arrow should go only there. So into this place. So basically we can continue the execution of the AND operation, but we replace the input on the input of arithmetic logic unit with the correct result, which will be stored into the register file in the 5th clock cycle. Same for the OR operation. It needs the value S0 read from the registers in the 4th clock cycle, but we allow this instruction to continue with the execution even with incorrect value read from the register. But in the 5th clock cycle, we know that the actual value which should be written to the register S0 is available on the output of the interstage register, which is mem to write back. And in the end of this clock cycle, the value is already available in the registers. And if we read the value during the 5th clock cycle from the register file, then there is a mechanism that we already get the correct value. We can imagine that writing and reading from the register file, that for example, we do not finish writing at the rising edge of a given clock cycle, but that we finish the writing at the falling edge. So basically in the first half of the cycle, and the second half of the cycle is available to propagate the new value to the result here. So in this case, we have no problem. So this instruction has no problem. But for those two, we can help and speed up the execution by adding so-called forwarding technique. For sure, if the actual addition takes more than one clock cycle, then it is not so easy. But if it is done this way, if the actual arithmetic logic unit executes the instruction in the single clock cycle, and only a register file read and memory reads, writes, and so on takes a long time, then we can, in the fact, take this value of the preceding instruction and forward it to the input of arithmetic logic unit. So it can execute a next instruction immediately. And there is a change of our design. So we have added there two multiplexers. So if there is no problem, then we read the one value from the register file second and then process it through the arithmetic logic unit. But if we find that the data which has been read from the register file, so we know from which register data has been read because we postpone the information from which register are data provided on the first and second output. And if we know that those registers are in use in this instruction, which is there, and we find that the memory stage writes to given register, so reg write M, and that this register matches one of those registers which are used as the input for following instruction, then we know that we need to forward a corresponding input through the memory stage. Same if we find the match between one of those registers which are used, maybe that some of them is not used if we use there the immediate operand, then we do not need to forward, but in another case we need. And we can check that this register can match the value of the register which is written to in the write back phase. And if there is a write active signal and write register matches one of the source, then we know that we need to forward the information this way to the input of arithmetic logic unit. And those way we have resolved the problem of dependency between two arithmetic logic instructions. Okay, we expect in this case that the delay on arithmetic logic unit is only single clock cycle. When it is more clock cycles, it is much more complex. So in this case, we have there the instruction add of those 222-333 to the register S0. We know that S0 is our register 5. It matches the value which is selected as the register which is read at the decode stage. But in this case, we do not stall the CPU, but continue with incorrect value read from the register to the next clock cycle. And in this case, the addition propagates to the memory stage. We know that there is a write. We know that there is a write to the register 8. And we have there already that value 555, which should be in fact read from the register to this location. But we have there a 000. But because we have found that there is this problematic situation, we switch this path to select the first input from the, not directly from the register file, but directly forward the value which is output from the arithmetic logic unit. Now for the next instruction, we again read an incorrect value from the register file, because a value is still here and it is not written back to the registers. But we propagate the value in this case, and we and it is not 666 because it is the AND operation, so it takes a 555 and does the AND operation with 1, 1, 1. So it is 1, 0, 1 with 0, 0, 1. So result is 0, 0, 1. So it is 1, 1, 1, 1. It is the result of that AND operation. And now there is the OR operation, and again it is incorrect value read from the second input register source 2. And if we go there, then we see that there is our actual instruction which stores the result 666 or 555, excuse me, register 2 with register 3, so it is 222 plus 333 is 555. It stores it to the register number 8, which is S0, it is correct. Now we have their instruction which does a OR of the S0, but it has read incorrect value 0, 0, 0 from the register file. But it is not problem because we have detected that there is this problem. So we activate the forward path from those 555 to the second input of the arithmetic logic unit, and OR of 555 with 444 is 5, 1, 0, 1 with 1, 0, 0, but it is in this case OR, so it is 1, 0, 1, it is correct, and we get correct result here, and the instruction continues. And then we have there the last instruction, but there is no problem with the last instruction because as you can see, the last instruction already sees the 555, which has been written to the register file and in the same clock cycle provided on the second output of the register. Oh no, it is first output. This is on the first output of the register file because it is that S8, S0, which is X8, and on the second one we have some S5, but it has a value 555 as well. So okay, it has the same value here. So now we see how the forwarding works, but we can get to the trouble. We have seen that we have forwarding from this location, output from arithmetic logic unit, to the input of the arithmetic logic unit in the fact. So it is output at the next clock cycle, and we provide it directly to the input of arithmetic logic unit. But if the instruction is load word, then we do not know actual result here, because at that moment we know only the address from which we want to read a value. And the actual value is known in the same for cycle, but after the delay required to access the actual value and read it from the memory. So in this case, we can forward the value from this location to the input of the arithmetic logic unit, for sure. But in the fact that way, we need time to access the value in the memory and then process it through the arithmetic logic unit. So if we do this kind of forwarding, then we need to lower the clock frequency almost by 1/2, or by 2, maybe even by 2, divided by 2. So at this moment, we again lose the speed up, which is there thanks to the pipelining. For this one instruction, the second one after the load word, we have no problem because the result is already on the output of interstage register in the write-back phase, and in this case there is no problem to forward the value to the input of the arithmetic logic unit. So what to do with this? For example, original design of Mips by Professor Hennessy defines that you are not allowed to use a directive value of the load word instruction in the next following instruction. Basically, this was declared as the forbidden. Okay, this is one option. Another option is that if we detect this situation, then we return to the previous snow technique and we stall the single clock cycle, the following instruction, and wait till the data are available. So now we try that stall mechanism to design, and what we need for it. So basically in this case, if there is this interdependency, we say, okay, we cannot execute this instruction because it wants to read S0, and S0 is provided as the output from the memory and will be available only in the 5th clock cycle. So we put there a bubble or stall, and in the fact we wait a 1 clock cycle till the first instruction advances to the 5th clock cycle and a write back phase. And in this case, we can forward the value. So we can look at it on the, again, simulator and on our design. So basically, this is our previous design, which can resolve the forwarding. But in this case, this kind of forwarding from here to there is not possible. So for this case, when there is a write to the register data from the reg write m. So basically, if we know that we need to go there not from the bypass, but that we want to go there in the next clock cycle from the output from the memory, then in this case, we know that if there is a match between the write register and the value of the one of those, or in the fact we can resolve it 1 clock earlier. So basically we can resolve it at the decode stage. So basically if we find that there is a write to the mem to reg, this one is active, there is a write, reg write E, and we want to write to this register which matches one of the decode registers in the decode stage, then in this specific case, we cannot allow the full speed execution, and we need to clear this interstage register. So basically, on the next clock cycle, so basically this instruction advances here, and on the next clock cycle, on this stage, a NOP instruction is generated, and we stop the clocks to those two registers. So basically we stop the advance of the program counter, and we stop the store of the fetch from the instruction memory. And this way we resolve the problem. So there is again the actual example in the simulator. You can read it from the web and test it on the simulator. So you can see we have there the load word instruction. It wants to set a register number 8. It wants to write to this register, and it is a write from the output of the memory, not that fast one, a bypass one. So in this specific case, if there is a match with the ret register from the register file, then we see that there is incorrect value, and we know that we cannot use a forwarding. So in this specific case, we provide a one stall cycle. We keep the end instruction here. It still wants to read a register 8. And this one has moved to the next stage. But in this case, we already have known a value which is 1, 2, 3, 4, and so on from the memory. And in the next clock cycle, this instruction advances to the execute, this one to the write back. And we can use a standard forward mechanism. We see that there is we switch to this one, but it is no problem because a multiplexer is fast. There is a value read from the memory. We see that we have a need in previous clock cycle to read the value from the register 8 as a first source. There, this one is written, so basically we remember this information. So we know that we can forward the value here, and at the price of one stall clock cycle, we have execute the instruction correctly with correct data, because as you can see, 1, 2, 3, 4 has got to the input, to the first input of the end operation, and on the second is that 1, 1, 1 from the register, which is not influenced by the previous code. So, okay, we have resolved all data hazards. And now what to do with the control hazard? It is a little more complex. Basically, if we decide that a branch, if we decide if we should branch or not to branch at the 4th clock cycle at the memory stage, then we need one more clock cycle to store the value into the instruction pointer, into the PC, program counter, and the next instruction would be read correctly. So if we have their instruction, compare T1 with T2, and if there is if those are equal, then, okay, in the assembly you would say go to the location 60, but actual machine instruction stores the offset, so it is 40 hexadecimal from this to 0, which is actual location of the instruction. Then in the fact we read the following two 3 instruction, and only then we start to fetch the instruction from the address 60. So we see that again there is a problem. We can resolve those problems that at this moment when we see that we want to branch here, that we basically move the result of this instruction here and to the program counter, and we remove the effect of those 3, basically that we flush them from the pipeline. So it is one option that we basically negate the effect of those by the flush, and keeping those instructions in the previous one by stopping the advancing of program counter and instruction fetch. Other option, which is used on Mips architecture, is that we have simple mechanism to compare two registers for the equality, because if you want to compare registers for the equality, you do not need a full adder for this. If you want to know the equality, then you can use a bitwise A and XOR, exclusive OR B, for each bit, and then a NOR to connect those results together. Basically, you know if exclusive OR gives 1 if there is a difference between those single bit signals, and if there is any of such difference, then it means that there is no equality. So one option is that we add there a second circuitry to compare the registers directly when they are read from the register file, and this one decide what to do with the branches. So this way we have lowered the number of the interstage registers from 1, 2, 3, 4 inside the loop. So this means a 3 which needs to be flushed and 1 which is there as a result of the sequence of the instruction, to only the 2 interstage registers. So in the fact we have there only a single instruction which needs to be flushed, and in the case of the Mips, they decide that we execute one instruction after branch unconditionally. So this way they really implemented a Mips as a machine with missing interlocked pipeline stages. So this is the name of the Mips, that basically it is a design which doesn't need to stall the CPU in any case. Okay, it has still one problem, that a condition in the branch can be dependent on the previous instruction, directly previous instruction. So in this case, we cannot compare the values where one of the registers should be set by the result of the ALU from the execute stage. So again, in this case, if we do not define in the definition of instruction architecture set that it is not allowed to use a directly result from the arithmetic logic operation for the following branch condition, then again we need to add a stall here. So in the fact, it is much easier if the processor can do stalls, even that it is not so efficient. And today processors usually resolve all hazard in the hardware, but compilers tries to schedule the operation such way that the stalls inside the hardware are not necessary. Okay, there is an example from our previous Qt Mips simulator of the Mips architecture. So in this case, you can see that if we have there a branch on equal and the register number 10 is used from the preceding operation, then we put there one stall and wait till the operation is advanced to the memory stage, and from the memory stage we can forward a value here. Again, more problem is if this operation is load word, in such case we need to put there even the second stall cycle. So it is quite complex, but you can be happy that we have switched to RISC-V, so you will not see a Mips in the exam. So it is easier. So there is what happens here, that we can, in this case, forward the value from write back to the no, it was forwarded one clock before. It was forwarded here. It was forwarded now from here. It should be forwarded. Yes, this one. There you can see that the switch is to the comparator is from this forwarded path. Okay, and then we execute already the correct instruction. So in this case, we have this one which is executed in the delay slot, and the next instruction already is the instruction which is the instruction on the target address of the branch operation. Again, the examples are in stat support repository and so on. So it is one option. Today processor has so long pipelines and executes so many instructions in parallel. In the fact, for example, PowerPC 970 has 250 instructions which are partially processed inside the core. If you speak today about the Apple CPU M1, then this architecture is able to decode up to 8 instructions in the single clock cycle. And it has partially processed instruction in the range of 600 instructions, something like 380 of integer and up to something like 250 of floating point instruction. So if you imagine this huge amount of the instruction, and if you delay the actual decision about a branch target address to some later clock cycle, then in the fact in the previous stages you do not have a single 2 instruction, but you have there something like 50 instructions. On the Pentium 4 there can be up to 100 instructions which needs to be flush if we do a branch. So in the fact you lose almost all the execution speed, because in typical business application the branch is taken by each 5th or 10th instruction. So the loss of the speed would be too big. So what to do with this? In this case, we can decide that we add there a branch predictor, and that branch predictor is then used to decide where to start the fetch the following instruction. So if there is a branch, then branch predictor predicts, okay, it is probable, for example, that it is loop and that we will go back. And in such case, we start to fetch instruction from the target address of the branch, even that we do not know if a branch is taken or not. And at the time when the branch instruction advances to the memory stage, for example, in our case, then in this case we compare if the decision of the branch predictor matches the actual result of the conditions here and actual target address which is computed here or here. And if it is matched, then the instruction which has been speculatively read from the branch target are executed. And if the condition is not met, then in such case we need to flush the instructions, and we inform the branch predictor what was the actual resolution of the given branch condition and given branch target address. Again, in a full depth, we go into this in the advanced computer architecture course, but we will have something a little about simple branch predictors on the next lecture. Okay, so I return back to our simple variant of RISC-V, where we do not have that second decision about branches here. We left the branches in the memory stage, and for this time we do not work with the predictor, and we look at this design as a final one for today's lecture. So what we have found, that thanks to the division of the previous CPU, which can process something like 1 million instructions per second, we have, with same components and some additional delays in the interstage registers and so on, we have got to something like 3 and something millions instructions per second in the case that there is no stall, and because we can make the clock faster. So in optimal case, we have a 3.4 times faster CPU than the previous design. And this is the reason why we have done all this complicated design, that we can speed up CPU execution. And if we look at our design, we look at it as a design which is somewhere inside the memory for the data, instruction, and so on. But we can look at it, and if we look even on the original non-pipeline design, we can put away the memories and add there and divide the CPU to the parts which we have seen in the original concept of von Neumann, almost 80 years or even more older architecture design of the CPU. So basically we have there a memory which is outside the CPU now. We have there a control path which controls the rest of the units and data path. And then we have there actual data path through the CPU where there is a read address, read data, write and read from the data memory. So in the fact, we can switch the internals and external world of the CPU and put a memory outside of the CPU chip. And in this case, we still have a Harvard architecture where we have one address and one data read for the instruction, and second address and possibly a data read or data written to the data memory. We can even combine those two buses together with some logic which stalls the CPU if it wants to read the instruction together with the write of the data or read of the data. But we usually have a separate cache for the instruction and data, so the actual design looks more like this Harvard, and then there is a unification on the second level of the cache, so it is quite often quite well matching. And if we look at our pipeline design, then we can do exactly the same and put memories away from the core CPU design and connect those memories through those signals. We should look what happens with the timing. So if we look at some interstage register, then there is a rule that this is a clock signal. At some time, there is a raise edge on the clock signal. So this is that event when the register takes the data on the input, remembers them, and for the next clock cycle, it provides the constant values on its output. But what can happen? To remember the correct value, the value has to be available in some advance with some setup time before there is a clock event, and it is necessary to have there some short hold time again after the clock event to capture the correct data and on the correct data on the inputs, and then after some time this TCQ, it is PCD, it is positive clock edge to Q, to the output. There is a stable result which is the value which is remembered from the input. So there are the inputs, and after some time we have a stable output for the next clock cycle. If we look to the combinatorial logic, CL, then the combinatorial logic has some propagation delay, PD, before the stable result is known on the output. Basically, it takes some time to distribute signals through the chip and logic gates to have the correct value here. So what it is necessary? It is necessary that we have there a stable value on the input, and we wait a time, so this is the delay here, and then we need to wait the time till the signal propagates through the combinatorial logic, and we need to finish with the correct inputs to have them in the correct state before this setup time, before the clock event. So at the end, we need to add those 3 times, and our actual clock cycle needs to be longer than those sum of those 3 times. So this is a definition and limit of the clock cycle. So basically, there is that time before the data are available on the output. Then there is some propagation through the combinatorial logic. It stabilizes, and at that time, we need there a reserve of setup time to next clock cycle. It is possible to build an asynchronous CPU which has no clock signal at all. It has been done, but it is very complex because each wire has to add, or each signal has to add the additional logic and signals, which informs the value is already stabilized to the correct value. And this way you can build a CPU which has no clock cycle and execute each instruction as fast as it is possible. But amount of the logic which you need to put in such CPU is 3 or 4 times bigger than for the simple synchronous design, and the actual complexity is so big and size that it will be probably slower than a classical synchronous design. So today all CPUs which you know are of this synchronous design. And there is another problem. There can be some skew that clocks are not delivered to all interstage registers and so on at the same time. So you need again to add there a reserve for the clock skew. And clock skew can be a big problem because, for example, there is a clock signal. This is one register which captures the input value. The next clock cycle, this value is used to compute something and store the result here into the next register. And if the delay on the clock, they're represented by the combination of a series of multiple inventors, is too long, then what can happen? That the value here is set before on this register is set and starts to change the stable value of previous clock cycle, and in the fact we do not capture the correct value here from the previous computation, but already change from this one propagates to the input of the next register. So it is one possibility. That at the capturing sequential, this one, the clock is delivered too much later than to this one which provides the result. And if the amount of logic here is small, then it is possible that we capture an incorrect value on the next stage. Another option is that clock arrives at launching sequential later than on capturing one. So in this case, again, we can capture incorrect value. It is possible that there is a local clock skew between those two directly connected registers, but there can be a skew on global level between multiple systems. And if you today want to do something more complex, you quite often use FPGA, programmable logic arrays or circuits and so on. For example, on Department of Computer Science, they use FPGA for processing of pictures. People at Department of Measurement are using a big science chip to process camera signal of Workswell, thermocameras, and so on. So you can get into the case that you have troubles with the clock distribution. And in the FPGA, it is done such way, or even in the complex design, that basically if we drive directly from the clock input individual circuits, then basically those one will be clocked in advance, and those further ones are clocked too late. So we can do so-called H3 when we clock connect clocks somewhere to the middle of the chip. Then there are clock buffers, and again clock buffers, and so on. So even if we want to, in the fact actual pin is somewhere here, that even that we want to drive this logic cell which is near to the actual pin input, we still drive it through the whole tree, that the distance or time distance, a delay between clock input and each logic cell is constant. And for the pipelines, if we want to speed up a processor more, then basically we want to divide the pipeline to the more stages. But if we have a common clock cycle, which we usually have for all the stages, then basically if we have some stages which are very fast processed and we reserve for them whole clock cycle, then we do not gain maximum throughput. So for this reason, we probably want to combine some blocks together, some stages together, such way that we have a pipeline balance. So for example, if we have this kind of the pipeline, which has long time to access instruction memory, even longer time to access a data memory, and then some operations which can be executed fast, then instead of limiting the actual CPU speed by the time to access the memory, we can prolong the operations through more stages of the pipeline. But in this case, the hazard and so on starts to be much, much more complex. So it is usually better, or okay, it is hard. It is better to observe, for example, cache, or we can have a pipeline cache that basically, in this case, we do the initial decode of the address, then in the second some access and so on, that we somehow can overlap the operations. So basically we divide, not to have it as a single operation, but as more operation. But anyway, we try to balance the pipeline such way that all the stages takes about the same time, and that we have it balanced and so on. And there are some examples, pipeline or small ARM CPUs, which are and MCUs, are about the 3 stages. Typical pipelines for the actual big CPUs are again something like 20. There was Pentium 4, which was 20, and at that time it was a little disaster. It was too much pipeline, so they, or even 31, so they returned back to something like 14, 16, but today, again, the length of the pipeline is increased to allow the faster clocks. Okay, and I think that we can discuss if we want to use branch stall or delay slot. Today, CPUs usually do not use a delay slot because it complicates the code too much, so they use a better prediction and so on. And okay, the development in this area is advancing very fast, and okay, we can look at it at advanced computer architectures, but for this course, it is required that you understand the simple, this simple scalar pipeline with 5 stages, which is okay, the standard from which most CPU design has started initially. So thank you for your attendance, and we will have 10 minutes break.